So now we have been working with I mean with numbers. So the features, it's just numbers. Now we need to work with an image. So we need to work with MNIST dataset, and the MNIST dataset it's a database for handwritten digits, which has a training set of 60,000 examples and a test set of 10,000 examples. So it's already divided. The digits have been size normalized and centered in a fixed size image. So the image size will be 28 times 28 pixels in gray scale. So now we have this data set, and we need to use a perceptron for multi-layer perceptron for solving this one. So 28 times 28, we will deal with each pixel as a feature, right? So number of input features will be 28 times 28, which is 720, right? Something. So we need to do the same using MLP classifier from SCK Learn neural network. We need to also find the confusion matrix. We need to find the precision, recall, and all those numbers with MNIST dataset. And remember, the pixel value, it's a number between 0 and 255. So you need to, I mean, standardized or normalized before. I mean the pixel value is a positive number, and it's positive number between 0 and 255. So you can just divide it. So the minimum value, in fact, it's 0, and the range it's 255. So if you want to normalize it, so just divide each pixel value by 255. So in this case, it will be a number between 0 and 1. So so I will just do you see the one which I'm sharing with you right now? So you just need to upload MNIST. I did it here from Keras, in fact, Keras.datasets, MNIST. So just from Keras.datasets, import MNIST, and so just now, can you upload MNIST dataset and use MLP for classifying it? We have 10 classes. In MNIST dataset, we have 10 classes, right? 0, 1, 2, 3, 4, 5 until 9. So we have 10 classes. And the size of the dataset, it's 70,000 line or 70,000 images. Now we need to build MLP for classifying it into those 10 classes. So X will be, I mean the features, X will be an image. The image's size, it's 28 times 28 pixels. And Y, it's number between 0 and 9. So I mean you have the program for I mean we have the collab already for for Iris. So just to try to modify Iris now for MNIST dataset. You can just unmute your mic and just let us discuss. I selected Keras this time to upload, I mean, MNIST dataset from Keras because, I mean, it's easy, but also can get it from sklearn. We will use here one hot encoding because, I mean, the output, I mean, Y, in fact, here when we upload it, so we have this line here, X train, Y train, X test, Y test, equal MNIST load data. I mean, we have those data, and it's divided into 60,000 for training and 10,000 for testing. But Y here, the target feature, it's one column, and it has the label of the classes. 0, 1, 2, 3, 4, 6, 7, 8, 9, right? So we cannot use it in fact in this way, and we need to use one-hot encoding. One-hot encoding, it means we need to convert this one column into 10 column using one-hot encoding. So it will be 1 when it's 0 and the 0 otherwise. It will be 1 when it's 1 and the 0s otherwise, and so on. So we call it one-hot encoding. And it's pre-processing. We need to do it for our model to train faster.
The one-hot encoding in this case has been used like internally.
No, not internally. We used here 2 categorical. Do you see from Keras utilities? I imported 2 categorical.
Okay.
2 categorical, it will make this one-hot encoding for us. So y train equal to categorical, y train, y test equal to categorical, y test. So it will do this one-hot encoding for us. And also, I mean, normalizing the data set. We use the normalization. We call it scaling, for example. Scaling, it means each feature we need to subtract x minus minimum divided by the range. Each pixel value here, it's number between 0 and 255. So the minimum is 0 already, right? And the range will be maximum minus minimum. Maximum it's 255, and the minimum is 0. So just dividing it by 255 will normalize it. So here I am, after uploading it, we try to put it in the correct shape, right? And after that, dividing it by 255. So each x will be divided by 255, and each y will be converted into one-hot encoding using 2 categorical, this function, nice function. So now we are ready. I mean, we are ready for training. If you will do this, you will be ready for training. You can go without, I mean, if you want to test the impact of scaling your features, you can just train it now without dividing each x value by 255, and you will see the difference. You will really see big difference. It will take much longer time, and also the performance will not good at all when you are using the same numbers. So we scale feature scaling. We do some feature scaling first by dividing each pixel value by 255, and also by converting y from categorical into one-hot encoding, because now it's categorical. It's 0, 1, 2, 3, 4. We have just labels. We need to convert it into one-hot encoding. When it's one-hot encoding, it will make life very easy for the neural network. And we will use here MLP classifier, right? So from sklearn.neural network, we need to import MLP classifier. For the metrics, we need to use maybe a confusion matrix, and also we can use we need to calculate also recall, precision, and so on. So it's called MNIST MLP. So I will open it here, MNIST. Yes, I will share. Yes. Now I have it. We have here the confusion matrix is a matrix, and it's the same. You can add precision score. There are many things, in fact. We just need to explore. Or, I mean, now we have our data set, and this is the size of the training set. So this is the size of the input features, 60,000 image, and it's 28 times 28. And this is a test set, 10,000. And of course, y and y, it's just one column. But if you want, we can print the size now with the shape of after one-hot encoding, print. You see now after one hot encoding, now it's 10,000 times 10. So we're converting it from one column into 10 column using one hot encoding. So we're changing it from one column into 10 column after one hot encoding, and we can plot some of those examples. Visualizing some, we are just visualizing it before, but if you want to visualize it, okay, sorry, I just forgot this one. Okay. Oh, because we converted it, in fact, we reshaped it. So so after that, we need to select a classifier, and I selected MLP classifier. I used also SGD, activation function logistic. This is the alpha value. I mean, alpha value, it's not the learning rate. It's the regularization coefficient. And hidden layers, I used the two hidden layers, in fact. So the first one has 100 units and the second one has 30. Maximum iterations 100. Verbosity, this verbosity to print out, I mean, outputs. The learning rate, it's 0.1. And this tolerance, I guess this tolerance, it's for I mean, stopping a criteria when you are reaching your goal. And fitting, and so when we train it,
If I can ask, how do we interpret the loss? For example, iteration 1, the loss equal to. What is the interpretation of this one?
I mean, yes, it's a lost function.
No. I'm talking about the results.
You are talking about what?
The results that we see, iteration 1, the loss equal, the iteration 2, iteration 4.
Yeah. It's this, for example, this mean squared error function. So we're calculating mean squared error over each epoch, right? So it's y minus output. So it's our target minus y. I will just call it target minus y square. It's 1 divided by m summation of t minus y squared, right? T, it's the target class, and y, it's the predicted one. So just to make, I mean, we calculate the difference between, this is the error. I mean, the error, we just agree that the error will be, the error which we need to minimize, it's the difference between the target and the output, t minus y. And we will make it squared because we need it to be convex function. So this value will calculate this value in each epoch. So this is the value which we are displaying here, in fact. At the beginning, we have lots of misclassification cases, and after adjusting the weights step by step, we try to minimize this error value by changing the weight values in the direction which decreases this loss value. So yeah, so do you remember? I mean, the cost function, which is, for example, y equal, it's mean squared error. It's just mean squared error between the target and the target class and the predicted class, t minus 1 square.
Yeah, I remember the loss function that we are using. I just want to make sure that if it refers to the same thing, the loss function, the error.
Yes.
Yeah.
So it's a mean squared error. We call it mean squared error, and the error here will be t minus y, target minus output. So we try to force the neural network to classify all cases as good as possible. So when there is misclassification, we count it as one error, for example. And of course, I mean, we take mean value, so we divide it by the number of epochs. In each epoch here, we are working with 60,000. So, and therefore it takes too much time here, right? So in fact, we are using SGD, so we are not using, I mean, of course, we can make it better if we can use batch, mini batch or batch learning, for example. But now we are using SGD, stochastic gradient descent. So in each epoch, in fact, we go to all examples, example by example, and we calculate the total error over the whole epoch. And this is a number which we evaluate, which I just present here. And it will be nice if we can plot it also. So, so please try to plot this error over the number of epochs to see how the error will, I mean. And after that, we will get the training set score, right? MLB.score, xtrain, ytrain. So we have this function in sklearn. So MLB score, it for the training and for the testing, because those two numbers are important to discover if you have some overfitting or underfitting. We predict for X test, so we get Y predict, and we can plot the confusion matrix for Y predict or Y test and Y predict, Y test and Y predict. So now we have the confusion matrix for training and for testing. And if you can see here for training, it's very well. In fact, it works very, very well, right? And the error also, we have the training set score, it's 1, and for the set score, it's 97%. And we have this tolerance, for example. So if the training loss did not improve more than this small value, which we decided here, it's 1 to the power of -4, for 10 consecutive epochs, we're just stopping. So when we select here this threshold value, this value, this tolerance, this one. So if the loss function did not improve by this value in 10 consecutive epochs, we just stop training. So we selected here 100 epoch, but in fact we finished at 28, right? So we finished at 28 because there is no improvement. In fact, there is no improvement for a number of epochs. So please, I mean, also go to this example. I mean, try to change those. I mean, try to play with it. Try to change. I mean, maybe number of hidden layers. It's too much, right? If you can, I mean, but remember that we have how many inputs do we have? I mean, we have this inputs 28 times 28 inputs, right? So we have 28 times 28 pixels, right? We selected the first hidden layer has 100, and the second hidden layer it has 30, for example. So just to try different numbers, try, for example, only one hidden layer, and try to see if, I mean, what will be the difference? Is there any difference? I mean, we will do this problem again using cross validation. We're just using now hold-on validation, and in hold-on validation, we divide the data into one for training and one for testing. But in cross validation, we don't need to do this, in fact, because we will divide the whole data set into a number of batches or number of partitions, and we will train it with k-1 and test it with k, and we will repeat this one for k times. And we do cross validation for just testing the performance of the model. It's just for testing the performance, and after that you will use the whole data for training your model. So should we take 10 minutes for, I mean, playing with this example and trying to make it different, for example? Okay. Yes, of course, Muhammad. Muhammad, he has a question. He is asking, increasing the number of hidden layers improve performance? It could improve, but it could lead to overfitting. Yes, because when you increase number of units in the hidden layer or the number of hidden layers, you will increase the model capacity. And when you increase the model capacity, your model, I mean, probability to overfit will be really very high. So you need to be careful. But for overfitting, there are many techniques for, I mean, solving this overfitting problem. And we have L1 regularization techniques, L2 regularization techniques, early stopping, for example, dropout. So there are many techniques for dealing with overfitting. But when you increase number of parameters, because when you increase number of hidden layers, you are increasing the model capacity. And when the model capacity increases, maybe the model will overfit your data set. The model will be able to memorize the data set, it will not be able to generalize. So if you see that, for example, in this example here, you can see that we have a kind of, because the accuracy here is 100%. I mean, in the training set, do you see? In the training, the accuracy is 100%, and in the test, it's 97%. Imagine that it's in the training set, it's 100%, and in the testing, it's 50%. It's clearly overfitting, right? because now the model has memorized, in fact, the training set. So so maybe the model is too complex, right? When the model is too complex, it will have the capacity, in fact, to memorize your data points instead of learning. So you can, I will just try with one hidden layer, for example, and I will try to train my model one more time. But of course, it takes too much time. And now I feel that it's much better than last time, in fact. If you don't want to see those, you can just set this one equal false or 0, for example, this one. Because we can control verbosity. We're using here, I mean, maybe we want, maybe some of you can help me also to solve it. We're using Colab, for example. Is it possible to use your local GPU? Now we're using this Tesla GPU, which is provided by Google Colab. But is it possible to use our local GPU when you are running? I mean, they mentioned the methods, in fact, for doing it online. So try to test it, please. For the home assignment, if we can talk about the home assignment, first home assignment, I just provided one slide. I provided it already to Blackboard. So we want to build a system to, we need to collect a good data set. I mean, this data set, I don't know if we can collect it really and take pictures of cars, but we need to collect a data set for plate license recognition, and also maybe car model, colors, and stuff like this. So we need to collect the information. So if there is a car passing some point, we can put a camera and we can collect how much information we can collect from this. So we need to collect a data for, there are some public data sets. I have been checking Kaggle, for example, for some data sets, but those data sets are closed, not public. So we need to find some data sets, in fact. So license plate data sets, so there are some data sets, but those data sets are closed. It's from Russia, this example, but maybe this one, I don't know. Can we download this one? Yes, we can download it. Very good. So there are some data sets, in fact. It's a 433 images of license plates. So there are some data sets, in fact, which is really very good. So we need to train a model to predict, to recognize those yes, and it's annotated, right? So we have those nice images. This is very good. I was thinking that maybe you can try to build our own data set from Olison, in fact. But there are lots of data sets. So, and it's annotated. And if you want to enrich it, if you want to add, it should be possible to add. So I mean, we have the image here and we have the annotation here, in fact. We can check it, D165, no, KL01. So I can share this link also with you, so you can download. Yes. Is there any way else to? Okay. So we have images and we have annotation as well. So anyway, we have lots of data sets. So I can share this link with you so you can download it on your computer and you can start working with this one. You can just search for any good data set. You can just download this one on your computer and you can work with it. So we need to build a model to recognize, I mean, maybe numbers, plate number, maybe also model, car model, color, maybe some information. I don't know if it is important or not, but we can try. So I can put it in, I mean, I can upload it to Blackbox if you want. So are you okay now with the example? So, so this is the accuracy. In fact, when I used one hidden layer. So can you plot the loss function, please? Can you try to plot the loss function? So now the accuracy, do you see? So the accuracy of the training set is 99%, 99.9%, and for the test it's 95.8%. If you go to MLP, I don't know if you can choose different. There are lots of parameters you can change. Of course, warm start. What is warm start? Warm start, it could be true and false. I mean, warm start when you want to use your model for online learning, for example. So we need to start from some initial values. So not from scratch. So when you train your model, you want to keep the weight values which has been optimized before. Early stopping also, it's one technique for, I mean, to terminate training when validation score is not improving, and if it's for overfitting. Loss functions, the current loss computation with the loss function, I mean. Okay. So do you have any question for this MNIST dataset? Any question for this one? We are working now with a full set of features. Now we are working with 28 times 28. So it's 28 times 28, 784 features. Can you imagine? So we are working with 784 features. We are not using BCA, for example. We can use principal component analysis. We can use some techniques to select maybe the most important 100 features and simplify the model. But now we are using the full set of features. model coefficient. If you want to get model coefficient, so what is this? Don't have anything here. Yes. So this is a test score. If you want also to, precision score, for example. This one we call it precision score. And it's Y test, Y predict. So we need to move this line here. So this one could be recorded also. So, okay. So should we go back to, do you have any question for this one? Yes, try to test it on random, okay. $784. So what is 784? So it's random, just random, a random array. Okay, and in all numbers, is it positive numbers? You need to be sure that it's between 0 and 1, right? Those numbers, it should be between 0 and 1. Can you share me the line of the code with, just share it with me, or just share screen, for example, or just write the line with this one line if we need to test it. So, but in fact, I tested it before, but with real numbers. So for, I don't know for the recognition for this license plate recognition, how you will do it. So test your model. Because I asked some people to write, in fact, we did it last year, in fact. So some people, they have been writing something, and we tested it with something written. Handwritten, not just a random. So I call it random digit, for example. Yeah? Okay. Why it's rand? What will be the output from this rand function? This one. What is the range of numbers? Okay, I will do it. So I just Ravi, he is testing it with this one. This one. What would be the range of this one?
Hello, Ibrahim.
Yes.
Can you hear me?
Yes, I can hear you.
Yeah, Ravi here.
Yeah.
It's a random array of, it's a random 1D array of 784, like digits.
Yeah,
so,
but numbers.
Yeah, it's between 0 and 1. I'm not sure. It just gives me some random output.
It's between 0 and can you generate number between 0 and 1?
Okay. Okay. I'll let me try. Okay. I just did it for just fooling around. I'll try it. Yeah.
But we did it last year. I mean, we did it last year. In fact, people were just writing because it's 28 times 28. So we cropping. I asked students, in fact, to test it by themselves. So they have been writing something. For example, you can write 2, 3, for example, and put it in 28. Crop it into 28 times 28 pixels, and using it for testing. So you can do it in the computer. You can try to in Paintbrush, for example, just write
So,
something.
but how do I like if I take an image of my handwriting, I need to get a 28 by 28 array.
Yes, we
So,
cropped it. I mean, we cropped it using. I don't.
okay.
You need to
Okay.
crop it into the same size, so finally it will be 28 times 28, and using it for testing. We did that last year, and it was in MATLAB, in fact, and it was working very well. So after training the model, it was working very, very well.
No, what if your digit or what if your entry is like not
the same? Not the same size.
What if I? Okay, so it's going to be a digit. It's you're testing it on. I'm trying to like sort of break the model. I mean, if I sort of write a digit, sorry, write an alphabet and test it with this ML, the MNIST training, then what would the output be like? Would it map it to something or would it just crash?
I guess because we don't have not else. For example, it should be possible to train the model using, they call it open set data set, for example. So for example, if we will get a new class which we didn't see before, so we can have one class which means I don't know, right? Because we have now 10 digits, so it will be classified into one of those 10 digits, maybe the closest one, for example. But we need, if you want to consider this in the future, we need something which I don't know. Do you know in MCQ questions sometimes you have A, B, C, and not any of those, for example, right?
Oh, okay, yeah.
We need to train. We need to, because now we have 10 classes, so it must be classified to one of those. Maybe I don't know the numbers, but can you generate a random number between 0 and 1? Can you check it? Random numbers in 1 0 in 0 1. So it's uniform. This one. So I guess we need to import here random. Can you do it? Anyone can do it, please?
Yeah, I'll try it parallelly. Like maybe we can move on to other things. I'll try to do this.
Okay, so just to try to generate a random number between 0 and 1 so we can test it. And no, you don't reshape. You don't need to shape it into 20. Yes, just flatten it. It should be flat, correct? Yeah, correct, Muhammad. So when you generate it, you can put it in 28 times 28 to use image show. Should be 28 times 28, correct? And can you do it, Muhammad? Andreas, can you generate a number between 0 and 1? So Andreas? Yes, can you give me the line of the code? Yes. Is there any one line? Of course, we can divide this one by 10. I don't know what is the range of. Okay. Okay, this one. Maybe this one. Yes. So I can find it, in fact. So oh my God. So maybe this is 28 times 28. Yes, sorry. Yes, but also it has some negative values, right? It has some negative values. Why negative values?
Ibrahim, I have shared a code, a line of code. You can try that.
Okay. Uniform. Okay. Because maybe this one is not uniform. Must be uniform. Yes. Okay. So we have this one now. So if we need to test it with a model, LP dot look, all classes are zeros. So do you see the output, Ravi? Ravi, can you see this output here?
Yeah, I can see that. So does that mean that it's not any number, right? It's
not
it
any.
didn't class it.
Yes.
Okay.
Maybe because yeah, which means it's a zero. I mean, it's a strange. Maybe we can use cross entropy, for example, or something, but it does not belong to any one of those classes. But you can try it. So you have this image. Do you see this one? It's 20 times 28. You can have something similar. Right. You can just write a number, and try to check it. Okay. And also we can add noise. In fact, one idea is to add noise. So you can generate a digit, and you can add noise to it, and you can see how much until when it will be able to classify it. So we can add some noise to the image. And you know, adversarial learning. So it's a kind of making the model confused. So we can add some noise to the image in a way to make it confused, right? How can we generate? I mean, there are some approaches for generating this noise, but you can start with this one. You have those images, for example. Now we trained our model. So you can, for example, select one digit and try to add some noise to it. And we will see until how much noise the model will be able to, I mean, to deal with it and to correctly classify this one. Because this one, maybe it's a 2. After some time, it will be more confusing between 2 and 5. And at some point, it will just say, no, I feel that it's 5, right? So, yes. Okay, so you can do it, Ravi, or Andreas, or Muhammad, or anyone. It will be really very good. So we have the accuracy in the training and in the testing in this model. I will share my screen because I guess we are okay. So we want to do it using Keras. Keras is very nice tool, very nice and very organized tool, in fact. And we will use Keras a lot in deep learning. So Keras, we need to know how to do. We will repeat the same problem using Keras. I mean, anyway we use the Keras. So we imported the MNIST dataset from Keras. Now we need to import a model. we imported also categorical, two categorical as from Keras. So how can we build MLB in Keras? In fact, we need to import sequential and dense layer. This sequential, it's like the frame, model frame, and the dense layers, it's the layers which we need to implement. So the model called the sequential, it's a sequential, not recurrent, for example. So anyway, this is the model, import models. We need to import sequential. And from this sequential, we will import, also we need to import from layers. So from models, we imported sequential. From layers, we import dense. And already we imported from utilities two categorical before. So we just need to import sequential and the dense. And we will solve the same problem, but in Keras. So I didn't include all the things from, because it's just the model, the classification model. So we need to find the shape. So the input shape. I mean, okay, we will start from sequential. So the model will be a sequential, right? The model will be a sequential. And to this model, you need to add some layers, right? You need to add some layers. So the first hidden layer, for example, I mean the input, we have input layer, but the input layer, it does not exist. In fact, the input layer, it's just a layer which transfer inputs into the first hidden layer. So anyway, we will start with this dense layer. This dense layer, it will consist of 350 units, neurons, right? We will use this activation function ReLU, and the input shape will be 28 times 28, right? So this is the layer. I mean, this is how we do it in Keras. In sklearn, it was very easy. I mean, it was very easy in sklearn, but this one, it's nice tool also Keras, and we will use Keras in deep learning. So it's important to know how can we deal with it. So first, we will start with a sequential, and we will add one dense layer. You can add more dense layers. So we added one layer which has 35 inputs. We have another hidden layer which has 50 units, right? Correct. We added an output layer. It's also dense, but the number of units will be number of classes, right? So the number of units, number of neurons, it will be number of classes. And the activation function, because this is the output layer, we will use softmax, because the softmax will calculate this cross entropy. So it will be normalized probability, I guess. It will be probability divided by the total summation of probabilities. So they call it normalized probability or something. So in this one in the middle, you don't need to specify an input shape, right? Because the input shape, it will came from the first one. Because this one in the middle, you just need to select a number of units, number of neurons, and the activation function. But the first hidden layer and the output layer, you need to specify number of classes and the input shape, right? So the input shape will be 28 times 28, and we have here number of classes. Number of classes, it will be the number of column in Y-train, for example. And the input shape, of course, it's this one. I can specify it here, in fact, or you can get it directly from the input from the X-train, right? So this is the model, and after that, we need to compile the model. So after building your model, so the first line, it's model equals sequential. We added here number of dense layers. We call it dense layers. We added 3 layers here. First hidden layer, second hidden layer, and output layer. But by the way, you can give it a name also. So you can give it a name here. You compile your model. So model.compile, you need to select the loss function. We will use here cross entropy, categorical cross entropy, the optimizer, and the metrics. Which metric you want to display? It's accuracy. It's so we just select accuracy. If you want to be sure that your model is fine, you can just use model.summary. So it will give you this table. Model type, it's a sequential. Layers, how many layers you have? We have 3 layers. This is the first hidden layer, second hidden layer, and output layer. So they call it dense 1, dense 2. But you can give it a name here, in fact. So you can give it a name here. So you can call it first hidden layer, second hidden layer, output layer. This is this one output shape. It's how many outputs? 350. because I selected here 350 neurons in this layer. So it has 350. This one has 50. This one has 10 because 10 it's the number of classes. If you want to, it has some advantage because it gives you number of trainable parameters. Do you know this hidden layer, for example, we have 350 units multiplied by number of inputs, correct? So we have here 350, but do you know how many inputs? Number of inputs is 28 times 28. So if you multiply 28 times 28 times 350, you will get this number, right? So I will do it. So 280 times 280 times 350. So it will be 274,400. Okay, plus the bias, plus 250. Okay, so I will share this with you. So do you see this one? So we need to calculate how many parameters in the first hidden layer. So the first hidden layer, it has 350 units, right? And we know this neural network, it has 28 times 28 inputs, right? Because each image is 28 times 28 pixels. So so the weight values, how many weights? So number of weights will be 28 times 28 times 350. Plus, remember, each unit has a bias, plus 350. So when you multiply this number, you will get this number, 274,750. Those are the number of trainable parameters which we need to train in our model. For the second dense layer, or the second hidden layer, it has 50 units. So how can we calculate this number? So it will be 50 times how many units from the first hidden layer? It's 350. So times 350 plus number of bias 50. So now we have 17,550. So this is the number of trainable parameters. For the output layer, we have 10 classes or 10 outputs multiplied by 50 plus 10. So it will be 510. So this is the number of parameters in each hidden. So and the total will be, this is the total number of parameters. This one will be the total number of parameters. So when you are using it in Keras, it will give you, in fact, lots of information, very nice information. Yes. Any question about Keras? Keras, it's important tool. We need to, we use the sklearn so far. So we need to use sklearn, we need to use Keras, we need to make comparisons. Some people, they use PyTorch. So those libraries are very, very good, in fact. I mean, Keras is very good and very easy, and it's important because we will use it a lot in deep learning. So this is the model. I mean, last time we used model fit. So this is the new part here. Model equals sequential. We need to import sequential from models. We need to import dense from layers. And you can just add as much layers as you want. So now our model consists of 2 hidden layers and 1 output layer, 2 hidden layers and 1 output layer. When you use model.summary, you will get, I mean, information about the model, the structure of your model, how many parameters, and so on. You need to compile your model, and when you compile it, you need to select the loss function, the optimizer, right, and the metrics, and you just go for Keras, and you will find all informations about those, and parameters. And after that, when you fit your model, we need to start training our model. So I will train my model using X-train and Y-train. You need to specify number of epochs. Batch size, because we can use, batch gradient, correct? When it's batch gradient, you need to specify the batch size. So the batch size here will be 512. So 512 examples in each batch. And verbosity, you need to define it. validation split, I guess it's 20% from the training theta will be used for validation. So the validation split 20% or 0.2, which means from the X train, Y train, from the training data set, you will use 20% for validation. Instead of using a model predict, I mean, we used, I mean, in sklearn, we used model.predict, and now we will use model.evaluate. So this is the test result. So using X test, Y test, you can just evaluate your model and so on, and just printing those numbers. So, so this is the results, and this is the loss function, this is accuracy, this is the cost, this is the confusion matrix in training and in testing. We have 10 classes. So for example, in the 0 class, for example, we have 5,914 of digit 0 classified as 0. So as I told you, we all time try to maximize numbers here in this diagonal. We do it for training and we do it for testing. But if you are writing a paper, maybe it's not important to do it for training, just maybe for testing. Yes.
Sorry, Ibrahim, if I can ask, for example, if we have used the PyTorch, the library PyTorch, do you think it's going to give different results than Keras? Or normally it's just like a question of what you feel familiar with, and you can use the library that you know better, and the results will be the same?
In fact, because maybe if you will use the same, I mean the same options, the same specifications, maybe you will get the same results, maybe, or slightly very small difference. But when we used here in this example, when we used sklearn, we just used it for stochastic gradient, right? So the result is different from batch gradient. Now, when we use the Keras here, we use the batch gradient, right? I know the difference here. I mean, this one is more accurate, correct? So in Keras here, it looks more accurate, but I mean, it's different parameters here. We use different parameters. We used here three layers. If you will use the same number of layers, same number of neurons in each layer, the same activation function, right? The same optimization algorithm is the same loss function. Maybe you will get the same number of epochs, for example. Maybe you will get the same. Maybe you will get the same results, right? So because it's a technique, and if they are just implementing it as it should be, maybe you will get the same results, right? So, but some tools are easy to use. People prefer to work with some tools. Some tools are older, some tools are new, right? So, so I like this Keras, in fact, because it gives us this table, and this table it helps us to understand many things from the model, especially when we go for deep learning, for example, and the transfer learning and stuff like this. It will be really very useful. It will help us to understand many things. Because in transfer learning, for example, we will import a block from another neural network. We will embed it here in this model. We will train only the last layer, or the last two layers, for example, for decision making. So I like it in Keras, in fact, because it gives us lots of informations, good control. I mean, lots of loss functions and so on. So and as you can see here, we are using here ReLU. So they are preparing us, in fact, for deep learning, because in deep learning they use ReLU and its I mean co-functions a lot. So so I think it's up to you. It's up to everyone to select which tool he prefers to use. But we should get the same results. So if you will have two tools, if you will have the same specifications, the same cost function, the same number of hidden layers, the same number of neurons in each hidden layer, if everything will be the same, you are supposed to get the same. If you are getting or initializing from the same random number, for example, you should get the same results, even if you run it 100 times. So, but it's a tool which we need to know, because this tool is very important, and maybe after 1 week or 2 weeks, we need to use Keras more, in fact, when we go for convolutional neural network and stuff like this. Yes. So should we take some time to go for this example? We can take 10 minutes, for example, so we can go for this model, and you have this. It's mnest underscore Keras in GitHub. Just to try to run it, and I will try to open it here also, so I can share it with you. And after that, we can take a break, or maybe we can just take a break. But please, Ravi, don't forget this one, please. So try to, we need to test our model. I mean, when we trained this one for MNIST, we need to test it. So try to make maybe small interface. We can have this small size of window, for example, which is 28 times 28 pixels, and just people can just try to write and test, right? If you can build small system, so people can just write by hand in the computer, we can just write like this, and we can test our model. It will be great. I mean, I guess we have people, lots of people from simulation and visualization. They are good in programming. Yes, okay. So Ravi, please do it, please. So you have the model. You just need to build something like this one, and people who can just write. If you have a touch screen, or if you can write by your mouse, for example, you can write 2, 3, 4, 5, and apply it to the model, and the model should tell us the results here, right? It will be cool. Thanks, Ravi. So I'm waiting it from you, Ravi. So now we will open the notebook for MLP Keras. MLP Keras, yeah. Yes, MNIST Keras, this one. So I use, as I mentioned, we imported sequential from Keras.models. We imported dense from Keras.layers. We used those functions before, confusion matrix. If you want to use, this is the same also if you want to use precision, precision score. This one from sklearn, precision, and recall, for example. But in Keras, I'm sure that in Keras there are more fancy stuff. So we need to run this one. Okay, we got this one. If you want to make some changes here, for example, you can just, for example, this CMap equal binary. Yes, so we have our digits. This is the model. So we use this 350. If you want to change, you can just change. I'm using Colab, but I want also if someone of you can try to figure out how can we use Colab with our local GPU, because in my computer I have a GPU. So I want to know how can I use this GPU. Yes, please, Ravi. So just to try to ask people to help you. So we can build this, we need to build this interface. And we have people can just write and add kind of noise. So it could be a project, it could be a home assignment, for example. I mean, for a group, for example, if they select to do it. So we need to have an interface, for example, so people can just write a digit, 3, 4, 5. We can do it also for A, B, C, D, and so on, alphabet. And adding some noise to it also, because I wish also to use it for adversarial learning. So if we can add noise, how much noise our model can accommodate, for example, can consider. So it's important, in fact, to start working with a GPU. How can we get access to our local GPU? It might be faster than the one which we have from Tesla, this Tesla GPU. So the batch size is 512. I mean, do you know this one also will impact the time used for training your model here? Because now we are dividing our data set into batches, and each batch size will be 512. I think we got some. Or close.
Ibrahim, if I can ask, everything that we have been doing up to now is part of the supervised learning because all our data is labeled.
Yes.
Yeah, okay.
Do you want to should we go for unsupervised, for example, one model or something?
I don't know. It depends on the rest of this.
So I got a question today about this error back propagation. So next time we will implement from scratch an example for error back propagation, the mathematics. We need to explain the mathematics behind it, and we will implement it for maybe a simple one, which can be used for iris classification, for example. We need to make it simple. And also, if people want to get something in unsupervised learning, it will be okay. So now we
Yeah,
have
because in the
Yes.
in the assignment we have the data set, but we don't know that if it's labeled or not labeled.
For license, for this car license plates,
Yeah.
it's labeled.
Okay.
So this
We
one
will
is
use
labeled.
supervised learning.
It should be
Okay.
supervised, yes. Because at the end we need to, if you need to build a system for the parking, right? So we need really to know. I mean, I cannot classify it if it is. We can classify it as red and black and white cars and stuff like this, but we need to read. In fact, we need to read the plates. So you need to check. I mean, check all options. Is it enough data set for training a model from scratch, or should we try to use some transfer learning or something, right? So please explore what kind of tools should we use. And also the data set, if the data set is not enough, you can take pictures by yourself. I don't know if it's, maybe it's illegal, I have no idea. But I have been thinking, because we had a small project also, was excited, and the idea was to, build a system for doing something similar. So you can just collect your data set by yourself, right, and share it with the rest of us, or you need to check also. You need to test if you will train a model from scratch or if you will use some transfer learning. So now we trained our model. We will run that part. So this is the confusion matrix, right? It's for the testing. Yes, we have two confusion matrix for testing and training, but we have a problem here. This one is not working. We have something here. CMap, I don't know, is it? So we have the but plotting it, it's a problem. I don't know why this one is not list color map. We need to import it here, maybe. So we need to import it, in fact. We just need to import this one. So we just need to have this one. So now we have our confusion matrix for the training and for testing. So just please remember to add this line here. Just remember to import this one here, or just move it here. So please, we can take some. Should we take, for example, 10 minutes? 10 minutes break. You can just. We finished anyway. We finished the slides for today, and also you need to know. I mean, before ending. I mean this one, because you need to check how can we save and load models. This is very important. So now you are building a model for the first home assignment for this license plate recognition, for example, and it will take time from you to train your model. And should you just throw it away and next time you need to train it from scratch one more time, or what should we do? So we need to know how to save train the models, and how can we import a train the model. You will train your model, you need to save it in somewhere, and when you are using it, you need to import model weights, use it, And if you want to update it at some point, you don't need to start from scratch. Just update and store it one more time. So don't need to retrain your model from scratch each time. So this is part which you need to explore, please. How to save and how to load your trained models. We will take 10 minutes break. Please go to this MNIST Keras and try also to change, those stuff. Try to make it different. And let us meet after, 10 minutes or 15 minutes, for example. So we will have also some examples as well. Yeah. Okay, so we will meet again after 10 minutes.
Hello, Ibrahim.
Yes.
Thank you for your lecture. I have a question related to assignment. Would you please give us more explanation about what should I do about assignment?
So you have the assignment. It's uploaded to Blackboard.
I don't have a Blackboard.
Okay, you don't have access to Blackboard?
Yes.
Can we fix it with Annalisa, for example? Is it possible?
No. At the moment, it is not possible for me to access. I'm a PhD student.
Okay. So no problem. The home assignment, I can send it to you, or I can share it with you now. So I will just.
No, I think you need to have access because I'm also a PhD student, but I have access to it. I think you have to fix it because the course is a master course anyways. It's not a PhD course. So you have to
I know. No. At the moment, I'm waiting for getting confirmation from UDI.
Okay. Yeah, I got it now. Now I got it.
Okay. So until this is the first home assignment, and I can send it to you, but we can just take maybe a screenshot, for example, or I can upload it here to the chat. Is it possible?
I've already sent an email for you related to assignment.
Okay. Yes. Okay, but this is the home assignment. If you can just send me an email after the lecture today, I can send it to you. So it's car plates recognition. We need to build a system for car plates recognition. We need to identify the plates number, for example. It's numbers and digits, so it's a mix between numbers and digits, and also maybe car model. We need to find the car model, maybe the color. And for collecting data or searching for a database online, there are lots of databases online, and I shared already with you a database from Kaggle, which has around 500 something or 400 something license plates. So this is a data set which we have, but you can just search online and try to find other data sets. And if you want to collect your own data sets, if it's not illegal, it should be okay, but I have no idea if it's, do we need to take permission because people will take, I have no idea, in fact, but search for any data set online and also use the one which I shared with you. I shared already with you link, and I will put this link also in Blackboard. And I have a data set which I downloaded. I can put it in Blackboard, but you don't have access. So just use the link which I shared with you today. This one from Kaggle. Do you see it?
Okay, thank you. And should I apply MLP technique in order to fit the model, or every technique is possible to find a solution?
Yeah, it's up to you to select which approach you want to go for. But MLP, it's similar to MNIST because at the end it's image, right?
Yeah. Okay.
But of course we will not use the whole image. We need to just focus on the part on the license plate itself, and so you need to explore what kind of tools we need to use. If you want to use MLP, it should be fine. If you want to use deep learning, it should be okay. But the amount of data which we have is not enough for deep learning, right?
Yeah.
But just explore, try to find if how because many people have been solving this problem already. So check how people solved it already. Is it possible to use transfer learning, for example, for solving it? Because I can import a model which has been trained for something else, and I can tune the model and I can use it for plates recognition here, for example. OpenCV, people also need to explore OpenCV, right? Because it's a nice tool also. It's in Python. So So OpenCV, it's a nice tool, right?
Yeah.
It's I mean, because now we are working with images, and so just explore, and I mean, don't work by yourself. I mean, try to make a group. For example, I mentioned in this home assignment that we can accept a report from a group, not more than 3 students in group, for example. So if you are 3 people working together, you will submit only 1 report, the 3 of you, and people can work together so they can achieve a lot in a short time. So if you want to work by yourself, it's fine. I mean, the amount expectations will be higher when we have larger groups. So when we have group of 3, expectations will be much higher than a single one who is working in the project by himself.
Yes, yes. Thank you for your explanation.
Thank you very much. So now we will take a break, and we will meet after maybe, should we meet 11:35 or 11:40? Is it okay? Is it okay to meet again at 11:40?
Yes, thank you.
Okay, thank you very much. See you.